guys, so this is video part 1 in a series of 4 about how to locate the solutions to basic trig equations. We're going to jump right in with our first equation, which says sine of theta is equal to negative the square root of 2 over 2. Now first, I'm going to notice that I'm only solving this in a single rotation around the unit circle, so between 0 and 360 degrees. And to get a sense of how many answers I can expect, I can graph both of these values and find when they're equivalent or when they're their point of intersection. So I'm going to graph sine x and negative square root of 2 over 2. When I graph that, I can see my familiar blue sine wave over its single period, 360 degrees, and this red line is representing negative the square root of 2 over 2. And it's intercepting, the graphs intersect at 2 locations over here, and based on what I know about the sine curve and how it passes through the 4 quadrants, it looks to me like this is happening in quadrant 3 and 4. Now I can identify that kind of straightforward and directly from the equation itself because I notice that there is a negative here. So because it's a negative value, and I know the quadrants in which the trig values are positive and negative, an acronym to help you remember is A SMART trig class. This representing all values being positive. Here sine and its reciprocal are positive. Here tangent and its reciprocal are positive. Other values being negative. Here cosine and its reciprocal being positive. Other values being negative. So the 2 in which sine is negative would be the 3rd and the 4th quadrants, because it's only positive in 1 and 2. So down here, so that confirms my suspicions based on this graph that I should expect solutions in quadrants 3 and 4. So I'm going to make a note of that whatever this angle theta is, whatever that angle is going to have to occur in quadrant 3 or 4. The next thing I'm going to do is to figure out the actual solution values is I'm going to figure out the reference angle. So the reference angle, which I'm going to abbreviate R angle for reference angle, would be the angle that would produce rad 2 over 2 as the ratio. Now you can do this if you know all of these trig values offhand. You can do that. For example, I know that sine of 45 degrees is going to give me square root of 2 over 2. But if you have forgotten those ratios, you could always draw the special right triangles. That's where these special trig angles come from. I have a 60, 30, 90 triangle, which is in a ratio of 1 to rad 3 to 2. And now I have a 45, 45, 90 triangle, which is in a ratio of 1 to 1 to rad 2. So to get rad 2 over 2, I'm going to have to use the sine of a 45 degree angle to obtain that ratio. So here's how I would go about solving this from here. Once I've identified both the quadrant and the reference angle, I have to put this reference angle in each of these 2 quadrants. What do I mean by that? I'm going to put a 45 degree reference angle in quadrant 3, and I'm going to put a 45 degree reference angle in quadrant 4. Then I'm going to interpret what standard position angles are going to end me in those positions. Now to figure that out, I know that in standard position, if I was to go around 180 degrees, I would land here on that line. And based off of a reference angle of 45 in that quadrant, I'm continuing another 45 degrees past that. So that means that this angle is terminating at 180 plus 45, which is going to give me 225 degrees. That's my quadrant 3 solution. That's one of these 2 answers to this problem. To get the other one, I'm going to do something similar. I know that in standard position, if I was to go all the way around to this position, that would be 360 degrees. And if I have this reference angle of 45 in the 4th quadrant, I'm really going 45 degrees back from 360. So this angle would have to terminate at 360 minus that 45 I'm going in the negative direction, which will give me 315 degrees. And that's my 4th quadrant solution, 315 degrees. Now we can actually check those by looking at our graph over here. I'm going to trace. I'm going to bring the calculator out a little bit so that I can check both of these answers. I'm going to check 225 degrees. Confirmed, that's one of the points of intersection. I'm going to check 315 degrees. Also confirmed, that's my 2nd point of intersection. So we have been able to identify the 2 values that satisfy this equation on the interval 0 to 360 by basically just identifying what are the potential quadrants based on the sine and what are the reference angles based off the ratio. So let's look at another example of this being done. Here I have secant is equal to 2 rad 3 over 3. Now for this problem, because I don't really know the secant values offhand very well, is I'm going to reinterpret this as its reciprocal ratio. Since secant is the reciprocal of cosine, I'm going to rewrite this as 3 over 2 root 3. And if we reduce this, if we rationalize this expression, it actually reduces to the square root of 3 over 2. So I need to figure out what values of theta will give me the square root of 3 over 2. And I'm going to do the same kind of interpretation. So there's no sign here, which tells me that by default it has to be positive. So I'm going to consider the quadrants where cosine is positive. And again, I'll use a smart trig class as my shortcut for remembering that. So all values are positive in quadrant 1, and cosine is positive in quadrant 4. So I have to be in one of these two quadrants. I'm either in quadrant 1 or 4. Secondly, I'm going to use my ratio. So for what reference angles will cosine be rad 3 over 2? Now you could go back to the special right triangles again, or if you know offhand the value for cosine. So for us, that's actually going to be cosine of 30 degrees. Cosine of 30 will give me rad 3 over 2. Given that value, I just have to put 30 degrees in each quadrant. So 30 degrees in quadrant 1 is very simple and straightforward because I'm going 30 degrees past 0, which is just going to give me 30. And in quadrant 4, I'm going 30 degrees back from 360, which will give me 360 minus 30, which is 330 degrees. Oop. Sorry about that. There we go. So I'm going to use my second solution is 330 degrees. Okay, so there's my two solutions for this question. So when dealing with a reciprocal, it's convenient to take its reciprocal so that you can look at one of the basic trig functions. And if you know, the better you know those trig values of special angles offhand, the quicker and easier these problems become. Let's look at one more example. Sine of theta equals 1. So now this is one that's a little bit tricky because 1 isn't coming from a special right triangle. I have to interpret this problem using the unit circle. So if you recall, on the unit circle, all of the coordinates, x and y, are equivalent to the values of cosine theta and sine theta, so long as it is a unit circle, meaning it has a radius of length 1. Okay, so on this unit circle, I'm looking for a location where the sine value is 1. Now, the only place that that's going to happen is right here. This would be the coordinate 0, 1. Okay, so it's positive 1 in the y direction. That occurs at 90 degrees. So there's actually, in this instance, only one solution. Theta has to equal 90 degrees. That's the only value for which the sine function is going to be 1. I could actually go back to this graph and check that. I'm going to clear out the square root of 2 over 2, and I'm actually just going to type in the value 1. And I will graph it. If you notice, there's only one coordinate that these two graphs intersect, and that is at the coordinate, I'll move this back, that is at the coordinate 90 degrees. If I plug in 90, I can see that is that point of tangency of this line to this curve, and that is where they are equal to each other. So that confirms my 90-degree suspicion. And if I look at the graph of sine, I can see that at no other point along this curve does it return back to 1. So it's only that one solution. So there are circumstances where we may wind up with one solution. We may need to use the unit circle to interpret that, but there are also circumstances where I may not wound up with more than one solution, and that's if I'm falling inside of a quadrant, not along one of those quadrantal angles.